Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'd like to introduce Srinivas Narasimham, who's visiting from CMU. Srinivas has been there now 5 years, 5.5 years. And he's going to be talking about light transport and both vision and graphics applications. Thanks.
Thanks for inviting me. It's great to be here. Okay, so when you say light transport, this term is used to mean collectively all the propagation of light rays within a scene. Okay, so traditionally and historically in computer vision, we are focused on a very specific kind of light transport, and that's a light ray from the light source straight goes to a scene point, and then that gets reflected back to the viewer. Moreover, you assume that the scene radiance does not change with distance as it travels from the surface to the viewer. But this is not the end of the story for light transport, right? So there's many mechanisms by which you have transfer of light from a source to the surface to the viewer. For example, it could be interreflections, right? So you have light rays bouncing between scene points, or it could be subsurface scattering, where you have light rays penetrating through the surface, scattering around, and then coming out of a different scene point. Or finally, you could have a volumetric medium. So surfaces are not immersed in vacuum. You always have a medium around it, so you're not going to treat the problem as 2.5D, but a full 3D problem, right? So it could be the atmosphere, it could be underwater, it could be any kind of a medium. So these three different mechanisms of light transport are what we can call global component, right? And they can result in very interesting and rich effects on the scene itself, right? So, and it's not as uncommon as vision researchers would want to believe it is, right? So it's everywhere. So if you are immersed in water, for example, or bad weather, your skin, it appears translucent, right? So marble, flowers, leaves, and all kinds of fluids and so on. So it's all around us, right? So we want to somehow try and understand the different kinds of light transport mechanisms, try to model, measure, and interpret them for vision and graphics applications. Okay? So what I'm going to do in this talk is talk about a few different applications. I'll start by looking at how to simulate the effects of the atmosphere as light is propagating through the atmosphere on imagery, right? So for example, if you look at images such as these, you see effects, visual manifestations of loss of contrast, dimming and blurring, and the glows around the light sources, right? So at night, if you go outside and it's misty, you see these beautiful glows around the light sources, right? So here what we want to do is try to simulate these effects for maybe video games or movies. So once you go and shoot a movie, and then you want to add these effects of fog and haze in real time. Okay? So let's try and understand the computational complexity here. So in order to simulate these effects, you not only have to look at the direct rays from the source and the surface, but also because you have a medium which has particles, right? You have light rays getting scattered from different directions and then reaching the observer. And this gives the feel of the glow around the light source, right? So the light rays go somewhere else and then get scattered towards you. So the same kind of mechanism can happen to a surface as well. So the surface doesn't get light from just one point in this area, but you have this entire volume that is lighting up the surface, right? And in this case, it sort of makes the surface look like an overcast day surface rather than a sunny day surface, okay? So you have highlights that are diffused out, shadows that are much brighter than usual, and so on. And the final sort of light transport mechanism is this slight blurring of the surface itself. Okay? So let's try and figure out how to simulate this very simple setup for graphics applications. So just to understand the computational complexity, it looks very simple, but computationally speaking, let's say this is your virtual screen or the image that you want to generate. And the viewer is looking at a single pixel, and you shoot out a ray out into the real world. And this is standard ray tracing, right? So this ray, you can divide it up into small chunks, let's say 50 or so chunks. And then at each of those voxels, you want to find the contributions of the light sources at that point. Okay? So then what you need to do is just march along these voxels and compute an integral along the line of sight. So this is what you want to do for finding the scattering from these light sources for this viewing ray. Okay? So then after this integral, you also imagine yourself sitting on the surface, and you want to do the same integration over a 2D set of directions. Right? So there's a whole lot of integrals that you need to compute here. Okay? So if you just do back of the envelope calculations, if you have a 640-480 image, can we dim the lighting a little bit? Thanks. That's good. So if you have a 640-480 image and you have, let's say, 4 light sources, and you divide up your ray into 50 voxels, just an arbitrary number, you get a total of 1.9 trillion calculations, which is quite a lot because adding fog and haze is sort of blurring and dimming lighting, but it's you're doing this very complex integrals, and as a result you're getting this many computations, right? So our goal is to somehow make it more tractable, in the sense that we want to get exactly the same solution as before. We don't want to create a trade-off space. So usual solution would be if you approximate the integral, you get lower accuracy but faster speed up, right? Here we want to actually beat that trade-off and say we want to get exactly the same solution but at a much faster rate. Okay? So for this, we need to understand the structure of this integral itself. Okay? So let's look at that integral, and I'm going to just sort of breeze through it quickly. So this is known as the Airlight Integral, and Koschmider, who defined this term, because this is very common, right? This is when you see outdoors, you see this sort of bluish haze on mountains and things like that. That's known as airlight. Okay? So you have this kind of an integral where, let's say you have a ray coming down from the source to a particle, okay, at a distance d, and you write its equation as I naught by d squared, which is the fall off from the point light source, and you have another fall off that is due to scattering itself. So most of the light gets scattered away, and what reaches is an exponentially decaying function that depends on distance. Okay? So at this point, something interesting happens. So you have light rays that turn, they scatter, and the intensity gets multiplied by some kind of a factor. Okay? Just like BRDF does for surfaces, here you have what is known as a phase function for particles. Okay? So once that happens, then you have light rays sort of going from that particle towards the viewer, and that again results in another fall off. Okay? So this is sort of the basic principle of light propagation due to scattering. Okay? Now, this is not the only ray that we need to consider. You need to consider all the other rays that are falling on this line of sight. Right? So that means then you need to compute this integral over a range of distances, that is, from the viewer to the surface. Okay? So this is the final irradiance that falls on the camera. Right? So now, this looks like a simple equation. Now let's try and write these parameters in terms of the parameters of the problem. What are the parameters of the problem? So you need to look at how far the scene is, the viewer is with respect to the point light source. You need to look at how far the surface is with respect to the viewer. You need to see this angle, and you need to also have the parameters of scattering. That is, this beta, which denotes the density of particles. Okay? So you have these 4 different quantities on which this integral is written.
Question.
Yeah?
Is k one particular function, or it's a family of functions?
So k can be a family of functions, like a BRDF. Okay. So, but you can expand it, for example, using Legendre polynomials.
Okay.
And you could have any number of coefficients.
Okay.
Okay? So one example versus Lambertian would be lighting going in all directions equally. You have an isotropic phase function that might be constant with respect to angle.
What are typical things like mist and so on?
So they are predominantly forward scattering. So they are elliptical,
Okay.
so around a point, and then most of it is forward scattering.
Okay.
So you can sort of parameterize that ellipse, the stretch of that ellipse, using one parameter.
Okay.
Okay, so if you write down this equation with the parameters of the problem, you get really an ugly looking thing. And there is no known analytic solution to this. And that's why in graphics you're trying to numerically integrate this equation. Okay? So what we did in this work, this was way back in 2005, we tried to sort of factorize this integral. We studied this integral a little bit more and tried to substitute different kinds of variables, played tricks with it, and we came up with a nice factorization that said this integral that depends on 4 parameters can be factored exactly equally, so it's no approximation, into a 3D analytic function. So you can extract out some of the functions out of the integral. And what you're left with is an integral that depends on 2 parameters. Okay? So and this integral is precisely the complexity in scattering. Okay? So once you have that, this looks like this. Okay? It looks like, sort of harmless looking function. So f of u comma v, the 2 parameters, is the integral of an exponent of u tan something. Okay? So if you just simulate this, it looks like a very smooth function in the parameters. Okay? So what you can do is you can pre-compute this once for all, so it doesn't depend on the scene. So you just compute it once and store it in your graphics hardware. Okay? And then what you need to do when you're rendering is just pick values out of this. Okay? Yeah?
So what's the intuition behind this 2D integral that's independent of the scene? I mean, is there some physical explanation?
So there is it's a little bit of weird explanation in some ways. So it depends on a particular transformation of these kinds of variables together. So one axis depends on the angle with respect to the viewing ray. Okay, and the other axis depends on what is known as optical thickness, which multiplies the density and the distance together. Okay, so both axes are physical quantities. But what you need is for any particular scene, you just pick the right pixel from this texture. So it's purely mathematical, that if you substitute variables here, you can sort of separate it out into things that change outside the integral and things that change within the integral. So once you have that, then your computation becomes extremely simple. So this A0 is this analytic function that I talked about, which can be computed very quickly. And you have to have 2 lookups of this texture. And you subtract these 2 things, you get your integral of that line of sight. Okay? So this makes it extremely fast. So you can store this. It's compact, so you can store this in graphics hardware. It's real-time, cheap evaluation, right? And you can arbitrarily change physical parameters. You can make it interactive. You can change any parameter you want, right? So all of this just requires a new lookup like that. Okay? So I should mention that this is now implemented in NVIDIA graphics card. So if you actually buy a PC with an NVIDIA graphics card, you can download their SDK and you can say add fog and haze, it'll do it in real time for any of your movies or video games and so on. So let me show you some of the videos here. Okay, so what I'm going to do is show a few different videos. The first one is just sort of a special case where you have just a set of point light sources like lampposts, and you want to see the glows around light sources as you're changing the amount of fog. Okay?
We start by showing a simple scene with 3 street lamps. Under clear day conditions, these are simply point light sources. The legend on the bottom left of the image indicates the frames per second, while that on the bottom right indicates the density of fog, or scattering coefficient beta of the medium, which is currently 0. As we increase the density of fog, glows appear. Artifacts in the glows and this and subsequent clips are due to video compression. As we decrease beta, the glows become smaller, and as we increase beta, they become larger.
Beta is just the density of fog.
Because of the attenuation of light from further sources, the glows become smaller as we move farther away.
So,
Why doesn't the whole gets blurrier? The whole seems very sharp as well.
yeah, this is just a CG scene where there's no depth of field effect or anything. So this.
I thought with fog would see some blurry effects.
Right. So in this case, what we are showing is just from the light source. We are not changing anything with the scene yet. So that's a good point to. The next step is to try and understand the effect of surface shading. Okay, so we looked at how light rays goes from the source to the viewer. Now we need to look at how they go from the source to the surface. Right. So here again you have this sort of 2D set of integrals. Right. And what we can do, for example, is you can take a BRDF and decompose it into, let's say, diffuse and specular. That is always done in vision. And then you can pre-compute tables, the texture maps for each of these components. Okay? So if you have a measured BRDF that has different components in spherical harmonics, you can do one for each. Right? So again, you will have a set of tables that you pre-compute. It could be 2 in this case. And then you start re-rendering again. Okay? So I'll just show you that video.
Our model can also be used to interactively calculate the change in surface shading due to scattering for the first time. Here we show a vase with both diffuse and specular components under clear day conditions. First, we see a brightening of dark regions at the bottom as we increase the scattering. Note that our method is fully interactive, allowing light sources, viewpoint, and geometry to all be moved arbitrarily. Here we move the light source, seeing the changes in shading. We now decrease beta to return to clear day conditions. As we increase beta again, note the diffusing of specular highlights due to scattering, followed by the dimming of the overall intensity due to attenuation.
So that's sort of just showing what happens locally on a surface. The highlights get wider, they get dimmer, and the shadows become brighter. Okay? Yeah?
The first video that you showed with the lampposts, you're not handling any occlusion of the lampposts or the light source. Like one of the lampposts would occlude the light source for a certain air pixels, essentially.
You're saying...
You see, when you have a foggy situation, you have these like lines in the fog where like...
Right. So if you had just a small field of view, for example, for the point light source. Right. So that's a much harder problem to deal with. So here we're assuming it's a point light source.
Okay, invisible from everywhere.
Yes.
Okay.
Yes. So we did some experiments. For example, you can come up with simpler approximations to create those shadow lines in fog. But traditionally you start with a point light source and then you cut off the angles that way. So, okay, so the full model looks like this. So you have the first model that looked at the glow surround light sources, and you have the surface shading. Okay, so you have 3 lookups basically, just in terms of computations. Two for the BRDF, 1 for the Airlight. Okay, so if you go back to our original setting where you had a 640/480 image and 4 light sources, you have this many lookups and this many analytic computations where you have this is a number of pixels, number of light sources, and this is the number of terms that approximates the phase function. Okay, so it could be 1 or 2 in general. So bottom line, this becomes 15 million instead of 1.9 trillion. The nice thing is there is no reduction in accuracy. It's exactly the same integral solution, okay, but arrived at much faster. Okay. So let me show you a video which includes all of this.
We have seen the types of effects our model can produce. We now show how these effects can be combined in a scene with complex geometry and 4 light sources. Again, we start with clear day conditions. Now we increase the scattering coefficient beta of the medium. As we decrease and increase beta, we clearly see effects like the glows around light sources and the change in shading on the vase and pillars. We can also see how the appearance changes as we modify the intensity of individual light sources. Now we show a comparison to the common OpenGL fog model. That model does not capture effects like the glows around light sources or the effects of scattering on surface appearance. We can change our viewpoint and move around the scene interactively. Here we walk through the corridor in real time.
So that was sort of an example where you have a complex scene, about 100,000 triangles, and most of the computations are for rendering the scene itself and not for the fog. Okay. So, and also we showed several different applications where if you want to do a pre-computed radiance transfer, how would you include fog in it? If you had an environment map of lighting, how would you change the convolution that is there for lighting between lighting and surface radiance? You have fog in between, right? So you could write it as a convolution between the lighting, fog, and the surface, right? So there's several applications that we showed by just, using this kind of an integral. So at this point, let me this is one thing that I always like to show, that this is the entire code that is required to do this. And so that makes it very easy to include in your shader code or fragment shader, for example, and add fog and haze to videos in real time. Okay. Yeah, that's that. Okay. So basically, this was just this was done in 2005, and I just like to show this because this gives you a way of how to computationally efficiently render things. But there's been a lot of work in trying to render volumetric scattering, for example, by Henrik van Jensen, subsurface scattering and so on. This, where computational complexity may not be the issue, but you want to create beautiful looking pictures. Okay, so there's been significant progress in that domain. It could be smoke rendering, wine, and things like that. But the next topic that I'm going to discuss is this issue of how to get the parameters for these rendering. So for example, what are the optical properties of wine or smoke, for instance, right? What are the numbers that you need to input to your algorithm to get those nice pictures? So typically, the accuracy nowadays is limited by the input parameters itself. Just like in vision, there's been a lot of work in measuring BRDFs, for instance, right? So you want to get as realistic as possible to the real world surface. You want to measure the BRDFs. So here, unfortunately, in volumetric scattering, there's not much work. Okay, so there's no table that I can go to in physics literature and plug out numbers from there for the stuff that we are interested in. Okay, so what we did was we tried to come up with a technique to measure the optical properties of liquids. A very simple setup. So you have a camera that's looking at a glass tank. So the glass is all anti-reflection coated, so that it doesn't have stray reflections. You have a bulb in this tank that is pre-calibrated, so we know the radiance of the bulb in all different directions. And what you do is you fill this thing with the liquid that you want. Okay, so we did experiments with lots and lots of things. We went to the local supermarket and we got wines, beers, cokes, everything. Okay, so my student who was working on this really loved this project because it was 23 liters of 4 different kinds of wine or something. So these tanks hold about 23 liters of the liquid. Now, one thing to note is that if you fill this thing entirely with, say, milk, you wouldn't see anything. So light transport at a basic level, you can think of it as blurring the incident light field, right? If you blur it significantly, you can't recover the properties well. Okay, so that's one of the major problems in light transport analysis, and it's being studied in physics for a long time. So if you look at milk here, and you have the light source there, you don't see the shape of the light source at all. And you were talking about the blurring. It just completely blurs out. Okay, so estimating things from such an image is ill-conditioned, and it doesn't have to be unique as well. Okay, so it's a much harder problem to try to invert this. So what we tried to do is we wanted to sidestep this problem completely and measure the liquids in a state where light transport is simpler. Okay, and one way to do that is to actually dilute the liquid. So if you dilute the liquid significantly or enough, you would be able to still see sort of the shape of the light source. There's not enough blurring there, but you have enough signal so that you can estimate the properties. Okay, so let me show you a video here of milk in this tank as I'm increasing the concentration. Okay, so we have filled this tank with water, and we add little by little milk to it. Okay, So, oh, sorry. That's the video. And you can see as the concentration is increasing, you can see the light source shape even now, but then it becomes more and more blurred. Okay? So until the point where you can't see anything and everything is washed out. Okay? So the idea is to dilute media sufficiently. Okay? Now, of course, this word sufficiently is the catchphrase in some ways, right? How much do you dilute? How much do you know? Milk you require a lot to dilute. For example, wine doesn't scatter much, so you don't have to dilute much. Okay? So we came up with a technique to do this. I'm not going to go into the detail here, but let's for now assume that you can find out how much to dilute. And then we have this kind of an apparatus. So focus your attention on this ray diagram that I'm going to show here. And this is a typical image that you capture. Okay? So if you look at a single scan line, this corresponds to a plane in the 3D box, right? And if you look at this single point, the brightness at this point is a result of an integral which is similar to the integral that I talked about in the first part. Okay?
You can no longer assume it's a point light source anymore, right?
No, it doesn't have to be point light source. So here we are just going to try and find the integral due to the rays that are going out from the source. So it could be done purely numerically. You don't have to use the exact same model that we used before. So a single intensity is a result of that integral. And if you scan this line, you're measuring all these different kinds of rays. Okay? You're measuring different ray lengths and the angles of turn. So a single image, now if you scan from top to bottom, would be all these angles, right? So a single image contains a lot of information. Contains a whole range of scattering angles. It contains a large range of path lengths of light rays, right? And you have combinations of these. So every pixel is giving you that information. Okay? So a single image has redundant information. Okay? And what we showed in this work is that you could, if sufficiently diluted, you could recover the parameters of the problem uniquely. Okay? So that was sort of the contribution of this work, that you could invert single scattering expressions. So then we went out and we got lots of different kinds of media. So alcoholic beverages, different kinds of coffees, fancy coffees, simple coffees, different kinds of milks, juices, soft drinks. We also got detergent and shampoos, anything that we could lay our hands on. And more seriously, we wanted to study ocean water itself. So this experiment I did when we went to San Diego during CVPR 2005, I think. And we got, we carried this glass tank to the hotel room, and we got water there, and we tried to measure.
Do you have any problems with the water being too clear? Or any of these mediums being too clear?
So I'll show you a space, the full space of liquids. And you have very clear and where you have murky and really murky and so on, right? So,
but if you had something that was like pretty clear, would you need a really big tank to get kind of that subtlety?
Right, absolutely. But the thing is that, yeah, of course, the image that you capture is not a single image, right? So you capture a series of photographs with different exposures, linearize it, get the best possible intensity resolution, and so on. So we typically work with 20 bits, effectively 20 bits of resolution. Okay, so these are some of the images that you get for different kinds of media. And you can see the different amounts of glows. You can see some of them don't have any glow. It's just attenuation, different colorings, and so on. Okay, so here's the set of images for just scattering media. So, espresso, cappuccino, orange powder, that's tang. Milk, we know that it scatters. But I don't know why one would want to find this out, but pink lemonade powder also scatters quite a lot. Okay, so on the other hand, you have images like these where you don't have much glow. There's not much scattering, but just attenuation. Okay, so these could be the Chardonnay wine, the Merlot, the Cokes, or the grape juice, and things like that. And ocean water doesn't scatter that much unless you have a lot of impurities in it. Okay.
It's from brown sugar, hot pots.
Right, so there is a alignment problem when you capture a lot of images. So it's just a issue of high dynamic range alignment.
And you didn't compensate for that?
We tried to do as much as possible to do it. But that doesn't turn out to be that much of a problem. So if you just, for this one, you don't really care about the exact boundary. If you have pixels here, you're fine. So if you want to plot all the liquids in this single plot, where on one axis you have the scattering power, on the other axis you have the absorption power. Okay, so we know that milks scatter quite a lot, absorb very less, right? So you could have, on the other end, you could have wines and cokes that absorb quite a lot but scatter very less, right? You could have, obviously, the Chardonnay course light would not do anything, Sprite would not do anything. So it's very less absorption, very less scattering. And there's this middle class, if you will, that has moderate amount of both scattering and absorption.
But when you talk about powder, doesn't it depend on the concentration?
Yes, yes. So it depends on how many teaspoons you put in this.
Right, so I'm not sure how you can just put the points up there when
Right, so that's normalized for the concentration. So everything is normalized for their concentrations. So the concentration, you can basically get the parameters out, and then you can extend it to whatever concentration you want. That will be more scattering or less scattering.
The orange juice really have that much of a, it looks clearer here than what I would envision orange juice actually looking like. Is that just because?
So this is orange powder. We have just put a couple of spoons in it. So it's not as much as orange juice, for example. Right. So the idea here is to actually show the table of numbers that we had in our SIGGRAPH paper, where we have the parameters. So the way to read this is you have the coefficients that are related to extinction or absorption, the coefficients that are related to scattering, and these are parameters of this phase function. Okay? And each one is for R, G, and B. Okay? So you have 9 numbers that you need to input to any algorithm. Okay? And then you can render with any favorite volumetric rendering algorithm.
The phase function, roughly speaking, again, is the elongation of the
Yes.
curve.
Yes. So it's just like the BRDF, but it's one parameter. Okay. So most of the phase functions, for example, if you see, most of them are 0.9 or 0.8 or something, so that means they're mostly forward scattering and elongated.
the dashes mean there are no measurements?
What is that?
The dashes.
Oh, yeah. I mean, so either it was totally unreliable that way. The scattering coefficient is 0 there. So the scattering coefficient is giving you the integral of the phase function. It's like the albedo of the surface. Okay. So if the scattering coefficient is very low, that's meaningless in blue.
So Coke and Pepsi pretty much absorb all the blue. So
Right. Right.
no way to recover it.
So anyway, just to say that the measurements were actually very accurate in terms of, so you get most of them with 1 or 2% error with respect to the measurement that we have made. So let me show you a few renderings. So the renderings I'll show you are with a cognac glass with the liquid in them and illuminated with this kind of a kitchen environment map. Okay. So the first couple of them are the wines. So you have the Merlot and the Chardonnay. So you have the deep red color and you have this sort of see-through Chardonnay. And you also have to look at the caustics, for example. So this doesn't have that much of a caustic, although there's this faint red thing, because most of it is absorbed. Okay. So here the caustic is much brighter because you can see through it. Okay. So you can do different kinds of liquids. So this is Yingling beer, which is brewed in Ohio. And for the longest time, I thought it was Chinese beer because it was one of my Chinese undergrad students who did this experiment. But of course, this doesn't have the fizz and so on that usually comes with beer or Coke, for example. But you can see the color of Coke is different from the color of wine, for instance, right? So, and this one is skim milk. Okay, so you can see sort of the soft appearance of milk. Now, just to show you these colors a little bit better, I'm going to render them in sort of an artificial environment where you have a single light source, very strong light source. And just focus your attention on the caustics. So here you have the beer. You can see this sort of bright orangish caustic. And you have a different kind of a caustic for Coca-Cola. Right? So depending on the absorption properties. So the fact that we need to get these absorption and scattering properties very accurate is that if you actually get them wrong in the second decimal place, milk would appear pink. Because remember, what we are doing is we are sending out 1 million photons through the volume and scattering them individually. If you get those scattering things wrong, eventually you'll get everything in a different color. Okay, so getting those parameters was very crucial, and that's sort of the contribution in this work, in that, you know, people could have input some random parameters, but you can't tweak them. You have to wait for a day or so to get an image back. So you can't just do this heuristically. So here's wine and orange powder. So this is some random concentration of the orange powder. And we did, you know, diluted strawberry shampoo, and this is a detergent in Pittsburgh. So you can see all of these nice red and blue caustics. And finally, since you have the parameters, you can play games like you can add 75% espresso and 25% milk to make it light brown coffee, right? So the idea is to not blend the images, but to actually blend the parameters. So that is the physically correct thing to do. So you're mixing the media, right? So, and I don't know why one would want to do this, but you, so in this case, we are averaging wine and milk, but we're not, you know, simulating any other chemical processes for curdling and things like that, but just as a fun thing. So here I wanted to show smoother transitions. We didn't want to go from water to wine, but the opposite direction. So so you should see in this video, it starts with wine and it slowly dilutes. So you can see as it dilutes, the caustic comes up. And it becomes pure water in this case. So all we are doing is just decreasing the concentration in parameters. And then it becomes sort of murky, and then it turns towards being milk. So again, the caustic disappears. And then finally, it goes from milk to being light brown coffee, and then until all the milk goes away to become espresso. Now you can see some of the, you know, noise in the rendering. So that's because you have to allow it enough time to get to that level. So, you know, you render these things for 2 days and then you lose patience and you show that thing. But it's a really computationally challenging problem to do this in real time. Okay. So just to sort of summarize this idea, we measured the parameters at these concentrations. So this is diluted wine. This is sort of murky water looking. This is milk. So that's beer and that's Merlot. And these are the real concentrations. So once you measure them, then you can increase them. So you can see the really soft appearance. And this is, I think, 100% fat milk. So you can see the really thick, soft appearance of milk. Okay. So here we looked at, you know, modeling and then measurement. Now I'm sort of switching gears on to try and do interpretation for vision applications. So during my PhD, I worked on this notion of vision in bad weather, right? Taking images passively and then trying to remove the effects of weather. So the nice thing to note that is that simple image processing techniques will not work because the effects of weather depends on the distances, right? So as a byproduct, you also get 3D measurements from fog. Okay? So assuming that the fog is uniform. Okay? So here what I'm going to be talking about is going underwater. So you have active illumination. So either it's at nights or underwater where you don't have natural illumination, where you can control your own lighting. Okay? The previous case of passive imaging was that, you know, you're stuck with whatever you have. If the image is completely blurred out due to fog, you cannot do anything about it. right? So if you have control over the lighting, you should be able to illuminate the scene in a more intelligent manner so that you can see far ahead. Okay? So one of the things that you should know is that you can't just use a very bright light source underwater where it's floodlighting the scene. So you have light rays going everywhere and everything comes back at you. Okay? So floodlighting is a bad idea. You can't really see anything there. So the reason for that is that you have the sensor viewing volume and you have the lighting viewing volume that is intersecting here, and that's lighting up. Right? So if this becomes larger, your contrast goes down. Okay? So a recent technique by Nair et al., there was a very nice paper where I'm sure you guys have all heard about it. This is using high-frequency illumination to remove global effects, right, to get direct. But that doesn't really work that, theoretically it's fine, but it doesn't do that well a job, in this case, because if you think of spatially varying this lighting, still the common volume is big. Okay? So for example, I'm going to show you an image where this is floodlit. I'm just placing a contrast chart, and you have some dilute milk in between, and you're capturing the image. Everything is just really bad, and there's no contrast. And if you do this direct global separation, the direct image looks like this. It's really noisy because what you're trying to do is you're changing the on and off pixels, right? But nothing much has changed in the image, right? So it's like subtracting two large numbers. You get noise, okay? So, and the image would just, the global component would just look like the original image itself, like a floodlit image. Okay? So what we want to do is to not actually spatially throw out light in all directions, but a better idea is to actually focus light in one sheet and then scan it. Okay? So in that sense, your viewing volume intersection decreases. Now, of course, this increases the time of acquisition, for sure. And it also says that if you have noise in your sensor, you need to have more integration time, right? So that you just have a small piece of light, right, if you don't have enough power. So it's a trade-off between how much acquisition time you were willing to sacrifice for accuracy. So what you can do is, so this brings us to the point of using light stripe range finding underwater. Okay, and this is, for a long time in underwater imaging, people have been trying to use light striping, but have not been successful because of the scattering effects. Right? So if you look at light striping in clear air, right? So you have a sheet of light hitting the object, and then you have this sheet scanned across, right? And you find the intersection. Typically, it's very easy. You threshold and you find this intersection, and you can reconstruct the surface. But if you look at what happens in a scattering medium, so the light plane itself lights up beautifully. Okay? So this is the scene that you would, if you go to a movie theater and you see the projector beam itself, right? So that's what is happening. So you have a light plane that is lighting up, and then you sort of scan it along, and one of those light planes looks like this. Now, if we try and model the brightnesses along this light plane using the scattering, and then try to find this intersection, you can create a template to detect the intersections more reliably. Okay? So this is much better, for example, in comparison to a floodlit image like that. Right? So what you can do is, so you can write the equations exactly as in the first couple of parts. So you look at a single light ray that is going through the medium, and you have attenuation along x and y, right? And you have the same alpha. So in the first part, it was k of alpha. Here, it's p of alpha. But it doesn't matter. It's exactly the same equation. And then you have, so in the phase function, you could write it as a one-parameter function. So p of alpha could be replaced by something like that, where g is your parameter. Okay? So another thing you need to think about is that this light goes and hits the surface, and you see this bump. And then that radiance gets attenuated by this distance. Okay? So these are simple equations for the scattering, and you combine the two. So you have something that is going like this, and then you have a bump. That's what it is. So if you look at it in terms of a plot, so when there's no scattering, you don't see the light plane itself, you see a delta function, right? And then as you increase the scattering, you get those things. Right? Now, of course, you can use this fall off to find the medium parameters, exactly like we did in the previous part. Okay? So you can do that. And 3D by triangulation or temporal analysis is similar to what you do in clear air once you detect those intersections. Okay? So the medium parameters, yeah?
Question. The leftmost image where it says no scattering, where are we seeing something that looks like flowers to the right of the stripe?
Right. So there is some kind of an interreflection, and it's water, but it has a little bit of scattering. So ideally, you should see a black image. Okay. So you have, let's say, this stripe is very bright, and it's actually sending light rays out to another object, and there's some interreflection as well. So once you get these parameters, then you can sort of create a clear air appearance of the scene. So you can undo what has been degraded. Okay, so let me show you a video for that.
When you have scattering, won't interreflection be more of an issue?
Yes, interreflections will be an issue, and in this case, we are sort of ignoring interreflections. We are only looking at scattering in the volume. Okay, interreflections across the scene points will be an issue, and that's my last part of the talk. Okay. So here, let me just show you a video.
Our light stripe range-finding experiments were done using a glass tank filled with scattering media, such as dilute milk, a projector, and a video camera. The desired objects are placed within the medium. The calibration of our setup...
I think calibration is quite straightforward, but...
When the tank is filled with dilute milk, the adverse effects of scattering are clearly seen in the floodlit image of the scene. Now, we show light stripe scanning in dilute milk. Notice the light plane itself becomes brightly visible due to scattering.
This video doesn't do justice to how beautiful it looks in the real world.
The intersection of the light plane with the object using simple thresholding. Our algorithm detects the intersections reliably despite the rescattering and reconstructs the 3D shape of the scene.
I mean, so the idea is not to create 3D reconstruction that much as it is to remove the effects of scattering. Okay, so as long as you get sort of approximate depths, you're fine.
It computes the appearance of the scene without any scattering effects, as if seen through clear air. Here we show a harder example with higher milk concentration. Notice the significant backscattering and loss of contrast in the floodlit image. We now show the light stripe scan. Notice that the intersections of the stripes with the objects are very dim and are almost invisible towards the end. Even in this case, our methods perform very well. Due to strong attenuation of the light planes and the dull reflectance of the green cup, the handle of the cup is virtually invisible in the input video and hence is not detected.
So basically, this is trying to show what the limitation is. If you increase the concentration significantly, you don't have any light going to the scene, right? So that's sort of the limitation. But it's, at least compared to flood lighting, it increases the visibility by at least 3 times. Okay.
We now show our results for a second scene consisting of a doll.
So here's a scene where there's lots of blooming and interreflection effects.
The light striping video of the scene shows complex blooming or blurring effects.
So as long as you can detect this better, then you're fine. So these are white, sort of whitish objects, so you have a lot of interreflections.
Again, our algorithm successfully removes the effects of scattering as shown on the right side. We now show the 3D reconstruction of this scene.
And there's no smoothing or anything done here, so every pixel is just reported just like that. Okay. So, that was one particular application, and we showed as part of the same paper also how to do photometric stereo. And it turns out instead of using 3 light sources, you need 5 light source positions to do photometric stereo of Lambertian surfaces underwater. So that was the result there. Okay. That's that. Yeah, that's the video is done. Okay, so this is just to show an example of a floodlit image versus what you can get if you're willing to wait until you can scan. But these scanning things can be done pretty fast. Okay, especially.
And when you said photometric stereo, that was with a scanning light, or you actually had
point? Yeah, this is just distant lighting.
Okay.
Exactly the same situation as before.
And the flood lighting wasn't disturbing the...
So it was very far away. So it wasn't really close by and shooting out rays in all directions. We made it a collimated source. Yes. Yeah, that is much of a toy example. This is actually being used underwater now. So they use the model and they try to do mapping of ocean floors and reconstruction and so on. But photometric stereo was much more of a toy example, more of interest to vision theorists, that instead of 3, you need 5, because you have more information through the medium, and it also depends on the depth.
Would there be any advantage to like the laser or something like that instead of having a stripe?
Again, this could be a laser sheet. So you could have a laser beam with a cylindrical lens, and it spans out a sheet. So the light source, in this case, we used a projector, but it could be any other.
So there's no advantage to having a point as opposed to...
Point would just make it, you have to scan it in 2D.
Right.
And of course, the brightness of a single point would be much lower. The power required would be much lower. Okay, so the final, just one side note as to how to place the light source in the sensor. And this is a recent thing that we found out, that it's not just that scanning a sheet of light is important, but where to place it. Okay, so if you look at the same old diagram where you have a common backscatter volume, you could place the light source close by. That increases the volume, right? Now, typically in underwater imaging, what they said was place it as far as possible. But there's also the issue of noise, right? So if you place it very far, you have attenuation and you have noise. So it turns out that there is an optimal solution to where you need to place the light source for a given visibility constraint. So tell me that you want 20-meter visibility. I'll tell you exactly where to place the camera and the light source. Okay? So you're just trying to optimize for the best image contrast, which is contrast times the signal to noise. Okay? So this would be, for example, just an example here, you have a glass tank with the dilute milk in it, and you have a camera and the light source. You see pretty much noise. Okay? So if you place it in the right position, without having to do any processing, you get a much better image. Right? So to try and control light transport before image formation is a very important thing in underwater imaging. Okay? So this was with a point light source. But you could do this with a laser range striping, for example, and you could get some kind of a strategy for striping. So it could involve both translation and rotation. Okay? And you get a much, much better image. This is the acquired image. So it's not processed or anything. So you can see, of course, you can see some of the vignetting effects and so on, but this image you can see all the characters and the the contrast gratings much better. Okay?
So are fog lights on cars in the right place?
No, turns out not. So it depends. The answer, the short answer is it depends on the amount of fog. So this is what I'm talking to Honda, and they want to actually move the fog light around adaptively. So given, huh?
It would actually move on the car.
What is that?
It would actually move on the car, like dynamically, or?
Yeah. So if the lights are just placed statically, right? So the driver is here, and depending on the fog, you can actually move it around, so to see much better. So there's no imaging involved here. So if you just tell the system how much far you need to look at. Now, of course, you can't do this for all situations, because some solutions may turn out to be that the light source would be outside the car, right? That you can't do. But it's interesting to note that if you can just play around with the positions of the fog lamps, you can see much better.
So is there an intuitive explanation about why certain angles are better than others?
So it's not in terms of this actual scattering property itself. It is, because the fog sort of backscatters quite a bit. So it's better to have an angle, for example.
Okay.
Right? So instead of having the light source right in front of you. So most of the light actually comes back at you.
So it's better to have an angle.
It's better to have an angle. Yeah, that's the reason fog lights are actually, well, the reason fog lights are lower is because there's not much fog on the ground. So you have fog layer that is sort of hanging in the air, and the light sources are actually below the fog layer. That's the reason they are placed so low. But the angle, the separation angle, just like in stereo, you have the two angles and you have a smaller volume. Right? It's exactly that principle. Now, by that assumption, you could place it very far away, but that's not going to work because you have attenuation of light.
But right now, the headlights were placed on the opposite, the outside, right?
Right.
So if you're saying further is better, why would you ever want to have to move closer?
That's because if you had lighter fog, for example. So the denser fog, you might have to place it slightly away a little bit. Lighter fog. So it depends on the density of fog.
So under lighter fog, you have less backscattering.
Right.
But what advantage do you get by moving the light closer to the viewer?
Because you have more sort of direct illumination of the scene. Right. So if you have just one lighting that is going this way, you want it straight ahead, right?
Because of shadows or back?
So you want to see, so what you want to do is you want to get most of the light to the scene.
Yes.
Right? So as the ray is going, it's attenuating.
Okay.
Remember. So you want the shortest possible path to the scene that is closest to you to get the maximum return.
Shortest in terms of this 1/r squared fall off.
1/r squared times e to the power minus something.
Okay.
So 1/r squared is just without fog.
Right.
The e to the power minus something is with fog.
Okay. So with moderate or light amounts of scattering, you're better off being closer.
Right.
Okay.
You might want to actually turn off the fog light that's closest to the driver.
Yeah, absolutely. Absolutely, absolutely. Or even, some vehicles have fog lamps on top. Whether that's such a great idea, I'm not sure. But it might be more of a style rather than.
Yeah.
But.
Right. Deer, Pennsylvania.
Deer, that's right.
So all of this is about just trying to optimize that expression for a particular visibility. So if you tell me it is 20 meters, we'll try to place it so that you get the maximum contrast out of it. Okay, the final part I'm going to talk about is the previous parts were sort of dated 2 or 3 years ago. This is much more new. Here we are trying to think about what kind of lighting that you want to use. So previously we looked at a point light source or just a bulb, for instance, or just a laser sheet, right? So in this case, there's lots of applications in vision where you want to use a projector, a programmable light source. For, there's been 8 ProCamps workshops already for different applications and so on. So one of the issues with using programmable lighting, it's great because you can program every pixel over space and time, but you have defocus, right? You have shallow depth of field of projectors, okay? So this is the first time we sort of studied the interplay between the defocused illumination and any global illumination present. Okay? So you can enable algorithms such as depth from defocus, projector defocus, or you can enable algorithms such as direct global separation in the presence of defocus. Okay? So let me show you what I'm talking about here. So if you look at this scene, right? So this is, a very bland looking scene. So but the materials are complex. So this is a candle. This is a polyresin bust. This is a impure marble, and this is a V-groove that is made of stretched cloth. Okay, and this thing is sort of a clay pot. Okay, that's the only simple material there. Okay, so what you do is, if you want to exploit defocus of the projector, let's look at just a point here, and you shine a pattern. Let's say a pattern of stripes across. And the projector sends it out in a defocused manner onto that point, right? Depending on the depth of the point. Yes? So if you shift that pattern across, okay, so you can see that this pattern may be better focused here than it is here. Okay? So if you shift that pattern across, the final brightness would be a convolution of the input pattern times the defocus kernel. So this is well known, right? But if you look at a point on the candle, which has subsurface scattering in it, right? So let's look at a point B. And in that case, you have not only defocus, but you have subsurface scattering. So you have light rays going into the surface and coming out. Okay, so you have this additional complication, if you will. So in that sense, we showed in this paper that the scene radiance can be written theoretically as input light pattern convolved with defocus blur, convolved with this new global illumination blur kernel. That depends on the intrinsic properties of the scene, the full 3D shape, the material properties, and so on. Okay? So if you just did depth from defocus by ignoring any of these interreflections or subsurface scattering and so on, you would not have this term, right? You would just have a convolution of two things. Now you think about Fourier transform of this. You have a product of the coefficients. And if you know the input pattern, you can divide it out to get the depth kernel. And that's how you do depth from defocus using active lighting. Okay? So if you do that, you get an image like that. Clearly this is wrong because the candle is actually inside the pot. And this is the depth of this pot is the only thing that is accurate. So everything else is wrong, right? So if you look at interreflections there, subsurface scattering, everything else is wrong. Okay? So what we did was, you have these two things acting together, subsurface interreflection with defocus. Okay? So at first glance, you would think that adding another kernel is going to make the problem harder, right? Because there's two kernels, you want to convolve them, how do you separate them out, and so on. But what we found was that if you change, let's say, the focus plane of the projector, then the defocus blur kernel changes much faster than the global illumination blur kernel. Because the global illumination depends on the intrinsic properties of the scene. It doesn't depend on where this projector is, right? So instead of doing this on one plane by shifting a pattern, you shift the pattern, move the projector plane, do it in another. So what happens then is that this blur kernel remains the same or nearly constant. These things change, and you can still get the depth out. Okay? So the two focal plane positions would be one, let's say, behind the surface. One would be in front of the surface. And you compute DFT as you're moving the pattern at every pixel. So this doesn't require the scene to have texture or anything. This is pixel by pixel. Okay? And you get DFT that looks like that. If you compute the Fourier transform of those convolutions, it's basically a product of three things. And the third thing remains constant as you're moving the focal plane. Okay? So you can sort of divide that out, and you get a depth measure that does not depend on interreflection, subsurface scattering, volumetric scattering, nothing. Okay? So here's an example. This is the example without doing this processing, so you get a wrong result. And you can now see sort of the dramatic change. Because now you can say that this depth is pretty close to this depth, irrespective of the fact that the subsurface scattering here is much larger than this.
Darker is closer?
Darker is closer, yes, I forgot to mention. Yeah, so the darker is closer, so this is the back wall, and you have the statue behind. Now, of course, here we're not trying to improve on the accuracy of depth from defocus. So there is a particular accuracy associated with depth from defocus, and that depends on the aperture, right? So what we are saying is that given that limit of accuracy, you can do much better in terms of subsurface scattering. Here's another example, and what we want to do with this is to try and understand translucency of materials. Okay? So my student went out and got all different kinds of candles and soaps. Right? They're pretty much aligned at the same depth, but their subsurface scattering properties are totally different. So you have different kinds of wax, different kinds of pigments with wax, and so on. Okay, different soaps. So here's what you get if you do the regular depth estimation. Right? So this, for example, is classified as the back wall, which is wrong. Right? So this, in fact, what you can think of this is that it's not a depth map, but it's a translucency map. It's actually showing translucency effects. Okay? But in our case, you get that, which is much more uniform across the different materials. So what we want to do is collect a lot of materials and build a database and come up with translucency factors, just like people did in BRDFs, where they came up with surface roughness factors. Here you can think of translucency factors. Okay?
You get the depth using just like a coated aperture type solution rather than doing 2 different takes, rather than changing the focus?
If you just change your aperture plane, you will not get that. If you just change your pattern on the aperture plane, that's what you're saying. Coded aperture, right? You will not get it because you have to change something that depends on the depth of every scene point.
So you can't make the blur unique enough. Okay.
So, yeah, I mean, the only way to dramatically change one kernel over the other is to move the focal plane.
Okay.
So here's another scene. So you have leaves and fruits and milk and so on. So I won't tell you how we get this sort of direct and global component. So if you look at the global component, you can still, by factoring out global, you got the defocus. You can factor out the defocus to get the global. Okay. So here's an example of how to get the global component irrespective of defocusing effects. Okay. So this would not be possible by just applying Shree's method. Okay. So you can see that the global component of milk is very high. The fruits, the leaves, and so on. So if you look at maybe a depth map obtained without assuming anything about light transport, you get this. So pretty much everywhere it looks wrong, actually. And whereas this looks much better. So you have this, the milk at the same depth. This is much behind, and these are much closer to the pot. Okay. So here's the final example. So this is an example where you have something made of velvet. There's fur. There's, for example, interreflections here, right? Very strange BRDFs, complex BRDFs. So just focus your attention on the interreflections here. So this is the incorrect depth map. So you can clearly see that this is wrong because of interreflections. So you can see that there. And we're not doing any special processing. It's just a pixel by pixel. It's just dividing 2 numbers. And you get that. So in this case, there's no effect of interreflections, either on that or this. Okay? So it's applicable to any BRDF or BSS-RDF. Okay? So at the end, maybe, how much time do I have? Have I overshot? Maybe? 1 minute? Okay, fine. Anyway, they switched on the light. Okay, so the last thing I just want to very briefly mention, and this is work with Alyosha and Jean-Francois, who recently received a Microsoft fellowship. Here we are trying to analyze the appearance of the sky. Okay, so in vision, we are interested in looking at, the scene for the right reason. You want to write detectors and segmentation and all of that, but nobody has really focused on the sky, which in many cases could be a big part of the image itself. So if you look at just this part, you have an idea that the sun is coming from maybe the right. Okay? So it turns out that if you try and analyze the appearance of the sky, which is basically because of scattering of sunlight. Okay? So you write the model for the scattering of sunlight. There is one already present in the physics literature, so you borrow it. That depends on the viewing direction and the sun direction. And just like the measurement part that I talked about, here you have lots of pixels with different directions and so on. So you can estimate the parameters of the camera, right, with respect to the sun. So you can, by looking at a sequence of images of the sky, let's say from a webcam, and this ICCV, we also have done something with a single image. So if you look at a sequence of images, you can find the azimuth, the elevation, and the zoom of the camera with respect to the lighting. Okay? So just to show an example, here's a webcam. So you can see that the sun is somewhere here, and it's going to move as I'm going to play the sequence. This is the sequence. Oh. Okay. So it's moving like that. So this is a camera looking east. Okay. So you can see there's lots of clouds and everything, so you still can take advantage of the blue part of the sky. And here's the estimated illumination with respect to the camera. So for this, you need to know the timestamps. So you need to know when it was taken. If you know the GPS, you get absolute orientation of the camera. If you don't know the GPS, you get relative orientation. So the sky is acting like a calibration target here. So here's another example where the camera is looking west. And so the sun comes from behind you and then sets in the evening. So you can see that it's set there. And here's the actual geometry. We initially, when we did this, we thought this is not going to be that accurate, but we find that it's surprisingly accurate. So it's about 2% or 3% error with respect to ground truth, where ground truth we define by doing another kind of calibration where you're just looking at the sun positions in the field of view. So that would be a straightforward calibration problem, right? 3D to 2D match, projection. So we compared with that, and we got very good results in that sense. And so we applied this for hundreds of webcams now. And we can do this very well with single images if the image has enough information. If the sky is big and the sun is not totally behind you, you can do it better. Okay, with this, let me just quickly summarize that volumetric light transport is the thing that has been ignored in vision for a long time for historical reasons. But I hope that I convinced you that this can have implications for a variety of fields: vision, graphics, oceanic engineering, and we did some research in medical imaging of endoscopy as well, and it's always used in astronomy, environmental monitoring, and so on. Thanks a lot.
Does anyone have any questions? Although most of you are meeting anyway, so just go to that. You guys about meeting any questions?
Yeah, sure. We had enough questions.
Okay. Great, thanks.